Hi, welcome to module 30. In this module we are going to look at several design problems. I am going to state problems in English and I am going to show you how to design state machines for this. So in the process we will also learn a lot of small tricks and techniques, so that when you design problems, if you are given problems on your own and if you are asked to design circuits for that, you will be able to do those things yourself. So let us start with an example problem. So the example problem seems to be wordy, but let us see what it is. So it says design a sequential circuit that produces a 1 on its output if it detects the sequence 101. So we have already done something similar earlier, but on seeing a 101 it should produce a 1 and the detector should keep checking for the appropriate sequence, the sequence 101, and should not reset the initial state after it has recognized the sequence. So as and when there is 101 that is coming in, it is supposed to check it, and whenever there is a 101 it is supposed to give a 1. So for instance, if your input sequence was 10101, then at the third cycle you see a 101, so the output should be 1, and again at the fifth cycle the output should be 1 because there is this overlap of 101. So you have to recognize that also. So this is the problem description, and I want to now think about this in terms of a state machine. So I want to show how to do that. So let us assume that I am going to build a state machine. So if I have not seen any input at all, so that is usually called the reset state. So I have reset, and usually we mark it like this, so that this is the starting state. So in the starting state what we have is, we do not have anything, we have not seen even a single bit so far. So what I can then remark here is, I can say that I am going to expect 101, right. I am going to name it like this, I am expecting 101. So once I know that it is a 101, I will then go and mark it. So now there are two possibilities. If the machine is starting with this state, so I do a reset to the circuit, the machine is going to start in this state. Now there are two possibilities. The possibilities are that I can get a 0 as the input here or 1 as the input here. So now if I start with a 0, let us say I get a 0 actually, then so I am expecting 101, but I am getting an input as a 0. So if I get an input as a 0, I am not getting a 1, so I can actually stay in this state itself. So you see this, so I am expecting 101, but I am getting a 0. So I cannot start the string 101 if it starts with 0. So if it is 0, it is as good as I am going to expect 101 itself, I will stay here itself. But if I get a 1, the output should be 0 because I have not seen 101, I have just seen 1, but I can go to a new state which says I am expecting 01. So you have seen 1 here and you are expecting 01 here. So we have now two states. So in this state now again there can be 0 as an input or 1 as an input. So if I get 0 as an input, then this is possibly a good thing, because if I get 0 as an input, so I know that I am expecting 101, I already came to this state, it is expecting a 01, and now it is expecting, it got a 0, so it has still not detected the sequence 101. So I can go to a state which says expecting 1, just 1. However, if I now get a 1, then there are choices, right, where should I go? So the easiest thing to do is, so this one is expecting a 101, so from this the whole sequence is 101, from here you are expecting 01 anyway. So if I get a 1, I could just loop back to itself, this is not going to change anything. So if I get 1 as an input, so it is possible that I get 1 as an input and after that I may get a 01, right. So this one has already taken me to this state, this one will keep me in this state itself, so that when I see the next 01 I can make other transitions. So that is what you have now. And now let us see, I have come to this state, in this state now again there are two choices, so I could get a 1 or I could get a 0. So if I get a 1, let us see what happens. So I have a 1, 0, and if it is a 1, I want to be allowing cases like these 10101 if I have a case like this, I want the output to be 1 here as well as 1 here, right. So the first one will, so the reset state is here, the first one would have taken me here, the 0 would have taken me here, and with this one, if I go back here with the output of 1, what this would do is, if I have a sequence like 1 0 1 0 1, then I can do 1 0 1 0 1 and so on. So this state is anyway expecting a 0 1, so if there is an overlap between one sequence 1 0 1 and another sequence 1 0 1, this state can capture that, so we can go there. What if we get a 0 here? If we get a 0 here, then we have the prefix, so we came with some 1 and then 0, we were hoping that this will be a 1, but we got a 0 here. So if you get a 0 from this state, it means you already saw 1 0 before and you are seeing the second 0 now. This cannot potentially start a 1 0 1 sequence. So I have to now expect a complete 1 0 1 sequence and not a partial 0 1 sequence, which means I have to go back here. So on a 0, I will output a 0, and what I will do is, so this state means I am expecting a 1, but if I get a 0, then if I go all the way back here, I can handle cases like these 1 0 0 0 1 0 1. Let us say I have an input sequence like this 1 0 0 0 1 0 1 and so on. You can handle such cases. So whenever there is more than 2 zeros, it cannot be a valid prefix for the 1 0 1 sequence. So immediately you can say that you can go back to this state so that you can continue from here. So this is a state machine. So what I have done is I have given some meaningful descriptions inside the state. I am expecting 1 0 1 here, I am expecting 0 1 here, I am expecting 1 here. So the moment I see a 1, I know that I have to produce a 1, but if I get a 0, I need to figure out which of these states I have to go back to. Now I can simplify this and instead write it as S0, S1 and S2. So instead of having names which are expecting 1 0 1 and so on, I can use these things S0, S0, S1 and S2, and I can draw the same transitions. So 1 0 1, so this takes care of what we want from the circuit, then there is reset and all the other cases that we do not want. So we can mark all of that, right. All these are not what we are looking for, you can mark all of that. So this, what you see in the bottom, is a state machine, is a valid state machine, right. So now this is a Mealy machine because the state along with the transition dictates the output. So for example, from this state, on this transition you get a 1, on this transition you get a 0. So depending on the state as well as the input, the output is decided. So this is called a Mealy machine, and what we have here is a Mealy machine. So this is the Mealy machine that I did. So you have the same Mealy machine described here with states S0, S1 and S2, and this you can draw the state table. So for S0, let us say I call this with 0 0, because there are 3 states, I will need two state registers. So I will call them Q1, Q0. So S0 is 0 0, S1 is 0 1, S2 is 1 0. So assigning these numbers to these states is called state assignment problem, and from the current state, based on x equals 0 or x equals 1, you have these as the next states and these as the outputs, and you can derive logical equations for it. So if I want to implement this with a D flip flop, then D1 for this assignment happens to be x bar Q0 and D0 happens to be x itself, and Z, which is the output, seems to be x and Q1. So you know how to do this, but I taught you how to do this in the last video. I suggest that you actually go and try this now, and you can see that these equations are the same. So if you use the sequence 0 0 0 1 and 1 0 for these 3 states, you will get these equations. So this is the Mealy way of doing it. Let me also show you the Moore way of doing it. So I am going to do the same circuit, but I am going to do it as a Moore machine. So in a Moore machine, remember, the states uniquely determine what the outputs must be. So again I will start with this one. I am expecting 1 0 1, but if I am expecting 1 0 1 I cannot produce an output 1 because I have not seen any sequence yet. So I will mark the output as 0 below. So within the state itself you will mark the output in Moore machines, and this is the reset state. So when if I am in the state expect 1 0 1 the output must be 0. Now if I get a 1 then I will go to the state expecting 0 1 and the output is still 0. From here if I have a 0 then I will go to a state which says expecting 1, the output is still 0, and now on a 1 I can go to the state, right, which is actually should produce an output 1 first of all, because you have seen 1, 0 and a 1. So at this point you can produce an output of 1, but if I want to handle cases like 1 0 1 0 1, so this is a partial sequence, right, 1 0 1 is ending this sequence, but this one is also starting the next sequence. So I will come and name this in a little while. So this takes care of various transitions, but it does not take care of all the transitions. So what happens if you get a 0? So you will still be expecting a 1 0 1, so you can put 0 here. If I get a 1 from here, you are going to still expect 0 1, so I can put a 1 here. So notice that these transitions do not have the outputs, they have only the inputs, because the states are supposed to tell you what the outputs are. So on the transitions you do not have the outputs. So on a 1 you can come back here. So what about if I get a 0 from here? So if I get a 0 now, it means that you got a 1 followed by a 0. So you got one or more 1s followed by a 0, and now you got another 0. So essentially you got 1 0 0 or 1, so many 1s and a 0, and that is not a valid, and if I get another 0 now, it is not going to start a 1 0 1 sequence. So I could as well go back here and afresh I have to expect 1 0 1. So I have to go back here. Now let us see from this state. From this state there are two choices, I can get a 0 or I can get a 1. So if I get a 0 from here, then I came in with a 0, I came in with a 1. If I get a 0 from here, right, and if I go back to this one, what it would mean is, so this is 1, from here I can again expect a 0 1, right. So if I expect a 0 1, so I will write that now, expect a 0 1. So if I get a 0 1, then again I can keep toggling between these two states and I can keep producing the output 1. So on a 0 I will go back here. However, if it is a 1, if I get a 1 from here, then I came in with a 1 and I am seeing another 1 now. So the only way to come into this state is the previous bit must have been a 1. If I see another 1 now, it is going to have a 1 1 sequence. This is not a valid prefix for 1 0 1. So if I get a 1 now, then I have to expect a 0 1, but I have to go to this state because I cannot stay in the same state because this will keep producing 1 as the output. So if I get a sequence of 1s, then let us say I got 1 0 1 1 1, you will come here, you will produce a 1. If you stay in the same state, you will keep producing 1 as the output, but we do not want that. Every time I see a 1 0 1, only then it should go to, the output should go to 1. So on a 1 if I go here, that takes care of the fact that this is, so both these states are expecting 0 1, but this state is different from this state because this state produces 0 as the output, this state produces 1 as the output. So if you have a partial 1 which is shared across two patterns, as pattern like 1 0 1 0 1, right, you will come to this state and you will keep coming back to this state itself. But if you have disjoint ones, if you have disjoint things like this, then you would come back to this state and that will give you the 1 0 1. So this is the general description of the problem, and again I can substitute S0, S1, S2 and S3 here, and that will give me a state machine. So that is what you are seeing in the next slide. So the Moore machine is essentially that. So it is the same thing that I did in the picture. There is a reset state here, S0, S1, S2, S3, and S3 on a 0 goes here, or S3 on a 1 goes here. S1 and S3 are both expect 0 1, except that one of them is producing 0 as the output and another one is producing 1 as the output. That is an important distinction. So because the states dictate the outputs, these two states have to be different. Again we have done some assignment here. S0 is 0 0, S1 is 0 1 and so on, and the output bit is given here. You can now go and derive the equations. So D1 is x bar q naught plus x q1 q naught bar, D naught is x and Z is q1 q naught. So what has happened is you have 4 states, this still requires only 2 flip flops. So if you already had 4 states in the Mealy machine, the Moore machine may have more than 4 states. So there is a difference between Mealy and Moore. So Moore machines may have more state registers than the Mealy machines, because Moore style may require more states to begin with, therefore more state registers than a Mealy machine. So this is the set of equations here. Again, I want you to go back and check this, and another thing that you can do is go and change the state assignment. So instead of calling S0 as 0 0, S1 as 0 1 and so on, what if you put some other assignment here? Go and see what the equations must be. Okay. So now let us move to other design problems. So before going to the other design, this is one thing that I want to show. So let us see this. There is a clock input that is periodic, and I have an input waveform that is changing at whatever time it is changing. I want to see if there is a 101 sequence. So let us see this Mealy output. So Mealy output would go from, so it will start with S0, which is the reset state. On a 1 it goes to S1, right? On a 0 it goes to S2, and on a 1 it comes back to S1 itself, and when it is in S2 it produces the 1 transition. When it goes from S2 to S1 it produces a 1 transition, and similarly when it goes from S2 to S1 it makes a 1 transition. And one thing you can notice is there is a glitch in the input here, there is an input glitch here. So from 1 it went to 0 and came back to 1, but because it is a synchronous machine, this 0 is not observed by the flip flops, because only when the rising edge of this clock comes in it is going to check the value or sample the value of input. So the state does not change. However, what has happened is because of this glitch here, the output may see a glitch. So in a Mealy machine, output can be directly controlled by the input. So a change in input, a momentary change in input can actually change in the can actually change the output. In this case, the state registers are okay, however the output has a glitch. So it should have been at 1 and then it should go to a clean 0 and stay at 0. It can momentarily go to 1 and come back. This can happen in a Mealy machine. However, in a Moore machine, so we had 4 states, S0, S1, S2, on S3 we produce 1, and this will stay a clean 1 because the output is dependent only on the state, and the state registers are kept for one whole cycle, right. They are not going to change the value. So on the rising edge the states will change and it will remain the same for one whole cycle. So you will see that the outputs coming from a Moore machine are stable for one full cycle as compared to the Mealy machine. Mealy machine may have multiple transitions even within one cycle. So in summary, Mealy outputs can change when an input changes, so it need not necessarily happen on a clock edge, and therefore outputs may have glitches. So however, if you make all the inputs themselves synchronous to the clock, then you will not have a problem. So if the input is asynchronous, for example this change from 1 to 0 to 1 was not synchronized to the clock, therefore you had this problem. But if the inputs were all synchronized, then this case will not happen. Or you don't, if you don't have any control over the input from the external world, you may be getting the input, you don't have control over whether it's synchronized or not, then in that case you employ a Moore machine. So Moore machine will have a steady output because the state dictates the current output. So and you're going to keep the state in the same value for one whole cycle. One thing that can happen is the output may get delayed by one cycle. So here you can see that in the third clock cycle, just as you are finishing the third clock cycle itself, the output went to 1, whereas here only in the fourth clock cycle the output went to 1. So there may be a delay in producing the output in a Mealy in a Moore machine. However, Moore machine will have stable outputs. So just remember this. So let us solve other problems now. So let us look at another problem description. A sequential circuit has one input and one output. When the input sequence 1 1 0 occurs, the output should become 1 and it should remain 1 until the sequence 1 1 0 occurs again. So this is a slightly more complicated problem. So the previous problem you could have solved with a shift register, this one is not. So if you get a 1 1 0, you have you produce a 1 and then it should remain at 1 till the next 1 1 0 occurs again, at which point it goes to 0 and you keep going back. So if I see the first 1 1 0, it should go to 1, the second 1 1 0 should take it to 0, the third 1 1 0 should take it to a 1 and so on. So this is what I want as a description. Let us see how to design a circuit like this. To do this, we need to first of all do a state machine. Let us see the state diagram. I start with the state A. Let us assume that this is the reset state. So on seeing a 0, I will remain in this state itself because I am supposed to be looking at 1 1 0. So on a 1, I go to state B and I will produce an output 0, and B on a 0 can come back to A because so from here you are expecting a 1 0 sequence. So on a, if I get a 0, I can go back and expect a 1 1 0, right. So I can go back here, and if I get a 1, I move to the new state called C. In C, if I get a 0 now, it means you are actually expecting a 0, so getting a 0 is good. So I will go to a state D, but I will produce an output of 1. If I get a 1, however, I will stay in the same state itself because you got 1 1, and if I keep getting a series of 1s, at some point it can switch to a 0, so I can stay in this state itself. So this state means I got 1 1 and I am expecting a 0. So you can, if I get another 1, it is only shifted by one more position. So it still got 1 1, you are still expecting a 0, so you can stay back here. Now you have produced an output of 1 for this transition, however. From D, D is now equivalent to A in some sense, because from here you are expecting the second set of 1 1 0 to come through. So when the second set of 1 1 0 comes through, so D will be similar to A. On 0 you will loop back, but the output will be a 1 because the problem description says the output should remain 1 until the second 1 1 0 occurs. So we have that. However, on a 1 you go to state E. So E on a 0 you can go back to D itself because it is again expecting a 1 1 0 sequence. Right. On a 1 you go to state F, and we now have to stitch F and A together. So F from a 0 can go to A, and now the output can go to 0. So this output went to 0 because you got 1 1 0, the first 1 1 0 will end up in D, the second 1 1 0 will take you to A, but at that point you have to make the output 0. However, if you get a 1 from there, you keep looping back at F itself. So A, B and C are equivalent to D, E and F, except that the outgoing transitions from A, B and C are all zeros, and the transitions from D, E, F are all 1s, and there is a transition from C to D which produces output 1, and from here it actually produces an output 0. So it's, you can see the symmetry between the top half of the state machine versus the bottom half of the state machine. Now I can do state encoding. There are 6 states, 6 states will require 3 flip-flops. So in general, n states will require logarithm n base 2 flip-flops, and the ceiling of that, the integer which is larger than log n base 2. So 6 states, log of 6 is 2 point something, and the ceiling of that is 3 bits. So I will need 3 bits to encode that, and let us say I have arbitrarily assigned it as 0 0 0, 0 0 1, 0 1 0 and so on. So I have given some increasing sequence for all of these. Now if I want to get a circuit out of this, then you need to do something more. So you start with 3 flip-flops Q2, Q1, Q0 which indicate the present state, and you have an input. You look at 4 vectors, right, 4 bits, and there are 16 combinations of these. So you enumerate all the 16 combinations. For each combination you decide what the next state must be. Right. So from the state diagram you can see what the next state is and what the output is. You can do this column and this these 3 columns marked blue and this column marked green, you can get that from the state diagram. Now if I say use the D flip-flops, then I taught you how to infer the D inputs from the present state and next state. So whatever you want as the next state, you place them in the D inputs. That is how D flip-flop works. So if I want 101 for the next state, I have to place 101 in the D input in the current state, only then it will become 101 in the next state. So now I can get rid of this next state, I do not need that. I will go and describe D2, D1, D0 and S in terms of X, Q2, Q1 and Q0, that takes care of the circuit. So I will suggest that you go and do that yourself. So the equations are shown here. So D2, D1 and D0 has some equations. S has an equation in terms of Q2, Q1, Q0 and X, and you can draw a circuit for that. So this is a circuit that can be used for this. So I suggest that you actually try and do this yourself and convince yourself that the circuit is correct. So now let me move to the next example. Design a sequential comparator circuit, that is to determine which of the two multi-bit numbers A and B of equal length is larger. Inputs are supplied in MSB first fashion. So let us first understand what the problem is. You are asked to design a comparator. Comparator will take two numbers as inputs and compare the numbers with each other and say whether A is greater than B or A is less than B, or it could be that A is equal to B in fact. So in this case, so this is something that we do in real world also, right? If I give you two numbers, how would you compare? If one number has more digits than the other, then automatically you will say that the one with the more digits is larger than the number with the fewer digits. But what if both the numbers have the same digits, same number of digits? I give you a 6-digit number, I give you another 6-digit number, how would you compare these numbers? You will start from the left side, right? So you will start from the left side. If the leftmost digit is the same, you cannot resolve whether A is greater than B yet. You will go to the next digit, you will again compare those two. If they are still the same, you will go to the next digit and so on, right? So the same thing, if you are given bits, if I give you two n-bit numbers and I ask you to compare, you can actually do a state machine for that. Let us see how that works. So let us say I have a state called 0 0 and I am going to get two inputs, one from A and one from B, but starting from the MSB first, right? I am getting the most significant bit first and I know that A and B are of equal length, right? So when I get A and B of equal length, so if both of them in the most significant position have a 0, it means the very first bit is not enough for me, I need one more. I probably need to go and look at the bit which is in the second from the left, or if I have both of them as 1, I still cannot distinguish and say A is greater than B. So in either case A and B I do not have a conclusion, so I will output 0 0 and remain in the same state. So let me do this on a piece of paper. So if I have an input like this and if I give you another input which is also like this, you will first compare these two numbers, you cannot distinguish between them, you go to the next digit, you compare these two bits, again they are the same, then you compare these two bits and so on, and if you exhaust all the 6 digits, you will stay in the same state 0 0 itself and produce 0 0. Instead, let us say at this point you have 0 1, you have a 7-bit number, up till here these two numbers are the same, but now you get on A you get a 0, on B you get a 1. If that happens, so on A you got a 0, on B you got a 1. If that happens, then you go to the state called 0 1. In this state the output, so you also make an output 0 1 which says A is, so which one is greater? So if this is 1, then A is greater, if the second output is 1, B is greater, but if both are 0 then both are equal. So that is the meaning here. So if it is a 0 1, B is greater, and the moment I decide that B is greater, all the bits that are going to come later does not matter. So even if I have any bits here after this and any bit here after this, it does not matter. It could be any sequence of bits after this and after this. This bit, this position tells me that A is less than B. So that is what is explaining this loop here. Once you have decided that A is actually less than B, then that is not going to change if you get more bits which have lesser weight anyway. So you will just stay in that. So the inputs become a don't care, you will always produce the output 0 1, and similarly if you have decided A is greater than B, there is one position where you discriminated A and B and A is in fact greater than B. The moment you have decided that, any number of bits that come in, they do not matter anymore. So you can just stay in that state itself. So this is a very simple comparator circuit. It compares one bit at a time starting from the leftmost side. If you started from the rightmost side, this is a very hard problem. because I see a 1 and 0 on the rightmost side on A and B. I cannot say that A is greater than B. I have to then go and look at the next bit, because that may actually change the weights and so on. So if I start with the MSB side, then this is a very straightforward state machine. It is a very simple state machine, and this is a very nice example because you get one bit as input at a time for each of the inputs A and B, and with that you are able to say whether A is greater than B or not. Then let us design a few other circuits. Design a bit serial odd parity checker. So it counts the number of ones in a bit serial input stream, and it asserts the output when the input stream contains odd number of ones. So if there is odd number of ones, produce a 1, if there is even number of ones, produce a 0. So that is what an odd parity checker is. So parity stands for the number of ones, so, and if it is an odd parity, the number of ones is odd. So that is a very simple state machine actually. So you start with, so if you do not have any inputs at all, then there are even number of ones because there is 0 ones, right. So that is even number of ones, you start from there. If you keep getting 0, it is not changing the number of ones, so you stay in that state itself. The moment you see a 1, you have seen odd number of ones, and if you keep seeing 0, you will just stay in even number of ones itself. In odd number of ones, if you see more zeros, it is not changing the parity, it will stay there itself, but the moment you see another 1, then you go to even number of ones. So this even and odd, even though the states are marked 0 and 1, they are actually looking at even number of ones and odd number of ones. So this state is for even number of ones, the state is called S0, and this is for odd number of ones, the state is called S1. So these blue numbers 0 and 1 are state S0 and state S1 respectively. This is not even number of zeros and odd number of ones, so do not mistake that. And you can now go and do a state machine for that. So I assign 0 to this state, 1 to this state, and I can get a state table out of it, and the equations for that also. So D naught happens to be X XOR Q naught, and Z, which is the output that is going to come from it, is Q naught itself. So there is only one single flip flop. The single flip flop can say whether if the flip flop has 0, it means it is odd, it is even parity so far, or the number of ones is even, but if it is 1, then the number of ones is odd so far. So it is just a single bit state machine. If you want to do T flip flops, the T flip flop is slightly simpler. So T naught is just X itself and Z is Q naught itself. So I suggest that you go and try this and convince yourself that using a T flip flop the logic becomes simpler. So this is an example where using a different flip flop seems to actually reduce the gate count. Here you would have used an XOR gate, here you do not need anything at all. You actually use one flip flop in both the cases, but you do not have any gates here, you have some gate here. So the kind of flip flop you use can actually control the number of inputs that you need. So as a final example I want to give this. There is a bus controller that receives requests from R0 to R3, these are 4 devices, and there are 4 outputs G0 to G3, and only one of which should be 1, indicating which device is granted control. So imagine there are 4 devices contending, maybe there are 4 computers trying to print onto the same printer. So one could be let us say the boss of the company, then one computer could be a manager, the third computer could be an assistant manager, and the fourth computer could be a regular employee. So all 4 of them, if they want to print to a printer, so you want the boss of the company to have higher priority over the other employees of the company. So you want to see who should get grant. There are 4 requests that are coming in, you want to grant permission to only one of them. So what we want is there are 4 outputs G0 to G3, and only one of them must be 1, because you do not want a printer to print multiple jobs from different users at the same time. So you want only one of them to be a 1. The lowest number device has the highest priority. So if R0 makes a request, then G0 must turn on. If R1 makes a request, you go and look at whether R0 has made a request or not. If R0 did not make a request, then you make G1 to be on, and so on. So that is what this one is, and assume that before servicing any pending request, the controller will remain idle for 1 clock period. So this is a very wordy problem. Let us see how to design this. So since we have an idle state, we need to have at least one state which says idle. So, if A is idle, no device is using the bus, then I will use the state B to say that device 0 is using the bus, state C for device 1 is using the bus, D for 2 is using the bus, and E for 3 is using the bus. So, the bus here means who is getting access to the printer, let us say. Now, let us see how the state machine itself would look like. So, this A is the idle state, and on A you do not give grant to anyone. So, you produce 0 0 0 as the output as long as nobody makes any request, which means if all the inputs are 0, then you stay in A itself. However, the moment R0 makes a request, which means R0 is 1, no matter what the other employees have, this is the boss, right, the leftmost is the boss. If the boss makes a request to the printer, even if other employees have request, you want to give access to the boss. So, from A you go to the state B where the access is granted to G0. So, G0 becomes 1, G1, G2, G3 stay at 0. As long as the boss has a request for the printer, the boss will get access to it, and only when the boss releases the request, right, once the boss releases the request, that is made by making R0 0, no matter what the other inputs are, we said we will remain idle for one clock cycle. So, we come back to the idle state itself. Now, let us see this transition. So, let us say that the boss is not making a request, the manager has a request, and it is also possible that the assistant manager and the clerk also want access to the printer. So, as long as the boss is not making a request and the manager has a request, no matter what the assistant manager and the clerk has, we want to give access to the manager. So, the manager gets a 1, the boss is not getting access, so that is a 0, and also the assistant manager and the clerk do not get access, and this will remain at this state itself as long as the boss is not making a request and as long as the manager wants the access to the printer. So, that is why you have 0 1 XX. The moment boss makes a request, let us say the printer is being used by the manager, the moment boss makes a request, that is from 1 XXX, you want to go to the idle state and the boss should be serviced, or the manager is done with printing, the manager removes 0. So, removes the request, which means he makes R1 0. In that case also you want to go to the idle state. So, the other two states are equivalent, right. So, let us look at the last state. So, you come to the state only when you know that the boss, the manager, assistant manager, none of them made a request and the clerk has a request for the printer. Only in that case you come and you will stay in that state as long as you are the only one, the clerk is the only one to make the request. The moment the assistant manager makes a request or the manager makes a request or the boss makes a request, you will go back to the idle state and you will have to service one of these three. In fact, if none of them makes a request, let us say the E is also done, the clerk is also done with the work, then the clerk makes the request 0, in that case it goes to the idle state. At that point it will remain in the idle state itself till somebody makes a request. So, this is a very simple state machine, but it is a very useful state machine because it shows you the notion of priority. The notion of priority can be handled in a very straightforward manner here by looking at what are the inputs and what are the outputs. So, what I will suggest you to do is you go and design a circuit for doing this. So, there are 5 states, these 5 states will require at least 3 flip flops, right. These 3 flip flops will take inputs which are R0, R1, R2 and R3, and the circuit should produce outputs G0, G1, G2, G3. So, go and think about how you will design such a circuit, and in this case the outputs are completely dependent only on the states itself. So, if you are in state A, nobody gets grant, if you are in state D, the assistant manager gets grant and so on. So, this is a Moore machine. So, go and check whether your output logic that you get is actually a function only of the state registers and not a function of the input directly. Go and verify that yourself. So, what we have done in this module is we have taken several design examples. We started with a problem description and I showed you how to do a state machine, how to mark the state transitions, and in some cases we also saw how to show the actual circuit itself. So, the general process is for synthesis of a state machine, you start from the English description, you go and draw a state machine for that, you do what is called a state assignment, you put so you find out the number of state registers, you do state assignment which says this state gets 0 0 as the label, this state gets 1 0 as the label, and so on. And once you do that, you pick up the flip flop that you want, you derive the excitation tables for that, use the excitation table, get the excitation for your circuit and draw the circuit. So this is the 5-step process. So this is a slide that I showed you in the last video. I suggest that you go back and look at the slide once more. This is the sequence for synthesis. So there are 5 steps that you need to do for synthesis. So this brings me to the end of this module. In the next module, we will do a few things related to the state machines itself. There are 2 more modules where I am going to talk about state machines in a little more detail. So at this point, I suggest that you go and do all these little pieces of work. Before you go to the next video, I suggest that you go and look at the contents of these 2 videos and ensure that you have done all the little exercises, and finally work out these exercises, convince yourself that you understand the ideas, and then go to module 31. So this brings me to the end of this module, and I will see you in a little while in the next module. Thank you.